So this weekend, I'm going to head out of town and go up north to do a race called the Michigan Mountain Mayhem. And as we do so, my partner who's going to be driving, I'm sure is going to be doing at least 80, maybe 85 miles per hour. Now, is 85 miles per hour, is that a vector? Which is the stuff that we're studying in this section. 85 miles per hour.
Scalar.
That's a scalar. Good. Excellent. It's just a magnitude. It's how fast you're going. But if you're traveling 85 miles per hour north,
then that's a vector.
That's a vector. Because what two things do a vector have? What two things does a vector have to have? Go ahead, Durade. You seem to be rocking on this.
Magnitude and direction.
Magnitude and direction. Excellent. So force is often portrayed as being something which is a vector. And we can see that from our illustration right here. A child pulls a wagon with a force of 14 pounds. The handle of a wagon makes an angle of 30 degrees to the ground. Express the force as a vector in terms of I and J. So let me draw this. And actually, I've already got it kind of drawn here. But I'm going to draw it on my sheet. And then we'll work on that. Express that in terms of I and J. So quick little triangle there, 30 degrees, and a 14-pound force. Of course, the United States is one of two countries in the world that uses imperial units instead of metric units. Be nice to use a 14-Newton force there, but that's okay. Let's call this our X and Y directions. So if I want to figure out how to write this or express this vector as, say, you know, xi plus yj, I need to figure out x and y. So let's do that. I'll start with something that involves my known angle, my known side, and my unknown side. So what trigonometric function wraps all these three things together?
Cosine.
Cosine. So cosine of 30 degrees is going to be x over 14, or multiplying both sides by 14, 14 cosine of 30 equals x. And we know what cosine of 30 is. That's square root of 3 over 2. So 14 times square root of 3 over 2 simplifies to 7 square roots of 3. So that's my force in the x direction. What would I do to find the y component of my force?
Sine.
Sine. So sine of 30 is going to be y over 14. 14 sine of 30 is y. So that's 14 times 1/2, or 7. Now here, this is no longer the imaginary number. What does I represent here? It represents a unit vector. Remember what those unit vectors are? And what unit vector is represented by I? I is 1, 0, and J is
0, 1.
0, 1. Excellent. Those are your unit vectors. So I could rewrite this as, let's see, 7 square roots of 3 times I plus 7 times J. And that's breaking things down into components. So you get your component in the x direction and component of your force in the y direction. Perfect. Perfect. Let's do some more work with vectors. Are we okay with this one?
Yes.
Okay, nice. Now, kind of backing up maybe a step and getting things to be more basic, let's figure out how to find a vector, find the point of a vector. And that's going to be from taking, for a vector from P to Q, taking the difference of these things. So if I want a vector that starts at P and ends at Q, then let me first copy down these numbers. P is 5, 4, Q is 7, 5. Now on the video that I had you watch, I think I was careful to talk about the notation here and the difference between something like this and something like this. This is the notation of a vector. It's no longer just a point, it's a line starting at the origin, ending at that point. So I want the vector PQ, vector starts here and ends here. To get that PQ, I'm going to subtract these, the latter from the starting one. So 7 minus 5 and 5 minus 4. And overall, I'll get the vector 2, 1.
Professor,
Yes.
why not 7? Because the P is the starting point, correct?
7 minus 5, 5 minus 4. No, I'm sticking with that. Well, let's take a look at it and see if it does what we expect it to do, right? So let me see if I can't draw something like this.
Also, you minus the starting point from the ending point.
The end point minus the starting point. So,
Okay. It makes sense now. Got it.
okay. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4. And I just need one more, 5. Okay, so let's look at these 2 points. So I want a vector that starts at the point 5 and 4, and then takes me to the point 7 and 5. So that would be over here, 7 and 5. So I want to start here and end up here. So that's going to be this vector, a vector kind of like this. That's not writing too good. Let's try this. There. Now we calculated that a vector 2, 1 would do the job, right? Let's see here. So vector 2, 1 is going to be this one. And I guess I've done a poor job of drawing this to scale, but you can see that if I take this vector and I start at this point, then it'll eventually get to that point, get to this point 7, 5. So the only thing that prevents it from being perfectly accurate is I didn't do so good of a job of drawing it at the scale. So yeah, I'm sticking with that. But since we've got this, let's do a couple other things here. One thing would be to find a unit vector that points in the same direction, but is only 1 unit long. And to find a unit vector, what you can do is take this vector and divide it by its length. So what's the length of a vector like this? So the length of a vector goes by this notation. Sometimes you'll hear it called the norm of a vector, or the magnitude of a vector, or the length, magnitude, length, or norm. All mean the same thing, and that is, how long is that vector? And you can calculate that length as the square root of x squared plus y squared. So for us, the length of the vector 2, 1 is going to be the square root of 2 squared plus 1 squared, square root of 5. Now, if I want a unit vector that points in the same direction, I can just multiply this vector by that length. So the unit vector would be 1 over the square root of 5 times 2 comma 1. Or you could just distribute that to both components of the vector and write it as 2 over the square root of 5 and 1 over the square root of 5. And what that'll give you is a vector that's not as long. In fact, it's 1 unit long. It points in the same direction, but the length of that vector is now 1.
You're okay with us having a square root in the denominator?
Yeah, I'm not going to worry about that. I mean, there's bigger fish to fry in this course.
Okay.
I think you'd even get away with that in my lab math. But if you wanted to rationalize it, it would look like this. You just multiply both the numerator and denominator by square root of 5 over square root of 5. Clean it up a little bit. All right. Thank you. Let me keep going. So we kind of did an example like this. Let's see, we did that one. Let's add a little bit more to this example. We'll just keep on going with this one just out of convenience. It'd be nice sometimes you're going to be asked to find the angle of a vector. And that is the angle that it makes with the positive x-axis. You know what, maybe we should do that for this one, just to do something a little different and get out of the first quadrant. So this vector points in the direction of 4 and -7. Can anyone tell me what quadrant that's going to be in?
First.
Oh, no.
All right, go ahead,
Fourth.
amend your answer. All right, 4th quadrant, excellent. So something like this, get this side of length 4, this side of length -7. So our vector is pointing from the origin to this point. So it's going to start out here and end up here. Beautiful. Now, let's see here. What we want to figure out what theta is. And theta generally is expressed as an angle between 0 and 2 pi or between 0 and 360, depending on what units you're going to work in. Either way, you've got a couple values here. I know the length of this side is -7 and the length of this side is 4. So if I don't want to bother calculating the length of the hypotenuse, I could just use the tangent. Tangent of this angle, I'll draw a theta here, even though it's kind of like a reference angle. Tangent of theta is going to be the opposite over the adjacent. So -7 over 4. And then what's theta going to equal? How am I going to solve for theta?
Inverse tangent.
Inverse tangent, thank you. So the inverse tangent of -7 over 4. And be careful what you're looking for. You're looking for something in degrees or in radians. Since my calculator happens to be in degrees, or excuse me, in radians, I'm going to get an answer in radians. So let's see. Inverse tangent of -7 divided by 4, something like that. Now that's a negative 1.05. All right, but chances are I'm going to want an answer between 0 and 2 pi. So, okay. That's not between 0 and 2 pi, that's negative. If I wanted a positive answer, here's how I can get one. All the way around would be 2 pi. I'm a little bit short of that. So way to get that is just take my answer and add 2 pi to it, because that'll take me all the way around here. If I do plus 2 pi, I end up with 5.23. Beautiful. That's my angle. Ooh, you want to be clever? Would you want to check it? You want to be able to show yourself that, hey, I nailed it. I got this answer right. You can do that. Because this angle should have a tangent of -7/4, which is -1.75. So if I take the tangent of my previous answer, and I'll do it this way, tangent of my previous answer, to get that, I hit the second key and then the opposite key down here, -1.75. Booyah, nailed it. How are we looking with that one? Doing pretty good?
Good.
Thank you. Let me keep going. Let's see. Let's work on adding vectors and talk about those. Let's talk about it just mechanically first. So I'm going to work with this example right here, where they give us a couple of vectors, v and w, and they want us to calculate 3v plus 4w. So v is 4i minus 6j. W is -3i plus 2j. And we're asked to find 3v plus 4w. So I'm going to rewrite this in different notation. I'm going to write that as v equals 4 comma -6, and w is -3 comma 2. And that's ultimately what this represents, because that's 4 times the vector 1, 0, and that's -6 times the vector 0, 1. If you add those together, you get this. They're convenient notations either way. I need to find 3v plus 4w. 3 is a scalar. So if I multiply this by 3, I'm going to multiply each component by 3. So it's going to be 12, -18. 4w is going to be likewise. Can someone tell me what 4w is going to be?
-12/8.
Excellent. And now all I need to do is add 3v plus 4w. So 3v plus 4w is going to be 12 -18 plus -12 and 8. The nice thing about adding vectors here is you're just going to add component-wise. So I'll add those two together, and I'll add these two together. And I'll end up with 0, -10 for my answer. So that's the mechanics of vector addition. But let me also show you another way to think of vector addition. What's actually going on physically, or at least graphically, what's going on. Before I do that, are we okay with this one?
Yes.
Yes.
Thank you. Thank you. Now, for demonstration purposes, let me talk about my swim workout from this morning. So I was swimming, and then on the way back, it's really tough to swim directly there because you're swimming into the sun. You're heading pretty much directly east. So let's take a look at it graphically and try and understand some of the components of my swim this way. And I think I've got a Desmos link here that I can send to you. So if you wanted to play with this or follow along, I'll dump that in the chat. And I shouldn't send that to just one person. I should send it to everybody. There you go.
I'm just wondering, Professor,
Yeah.
how do you have that much energy to do that entire thing?
Years of training. Thank you. Yeah, years of training. So, and a bunch of good friends that I do this with. So, and the one of them was the guy I was speaking with in Spanish. That was kind of fun. So here's the first leg of my swim, kind of idealized. I swam from, we'll call it the origin to the point 9.3. And then I'm like, okay, I'm close enough to shore that I better start sighting, and I see I got to change my angle a little bit. So I change my angle and head back to shore. Let's get rid of this and take a better look at what we've got. So what we have is the addition of two vectors. So it's this one here, the purple one, plus the orange one. That takes me to my final point. One thing that I can show you is that it doesn't really matter what order you add the vectors. I could have done things this way and then this way, and I still come up with the same point, right? So that shows you that vector addition is commutative. You can add them in either way. But what I want you to think of and what I want you to come away with here is the result. And the result of adding two vectors, so let me just get rid of these for just a second. The result of adding two vectors is going to be this right here. That's where I finally ended up. But you can think of it as completing the parallelogram right here. So just drawing two parallel vectors, and then what? Where you end up, the resultant is just the diagonal of your parallelogram. That's what adding two vectors actually is. It's the result of adding those two and finding, that diagonal. So there it is. All right. Let's look back at a few examples of adding vectors to finish this up. This one is a good one. Actually, you know what? I should probably do a couple of these before I do that last one. So, let's look at this one. We've got the vector W and the vector V. We want to add those together. So they've given you a choice of several different diagrams, and you're to pick which one represents, let's see. Well, actually, they want V minus W. No, I want to do V plus W. Let's do this one up here. Same kind of idea. Here's vector V, here's vector W. You're going to add these together and see what you get. So, vector V starts out at a point and takes you due east, and then vector W takes you east and north a little bit. But is the resultant vector going to be pointing kind of opposite? Are you going to end up here? Does that make sense? No, it doesn't.
No.
It doesn't look like the resultant there. So, nix on that one. How about the next one? Let's take a look at that. So again, you start out vector V takes you east, and then vector W takes you a little bit north and east. And they call the resultant vector V plus W. That's going to head along this diagonal, or what would be the diagonal of the parallelogram. How does that one look? Does that one look a little bit more like what you would expect for V plus W?
Yes.
Yeah, absolutely. And this last one, boy, this is totally blown out of scale. What they drew for vector W doesn't look like vector W at all. But then they get this little piece right here. That's actually going to be, I don't know, I think it'd be closer to V minus W. That's what it'd be closer to. Or V plus W minus W, something like that. This one's a mess. That one's not the right one either. So, yeah, what you're looking for is going to look like what would happen if you complete the parallelogram. Now, a lot of your examples in the book are going to look kind of like these. So let's do a couple of these. They're going to ask you, is A plus B equivalent to vector F? Let's see if we can't answer that. So vector F takes you from this point to this point. Let's try it with A plus B. If I start out at the same point, if I did vector A, that would take me up to here. And then vector B would take me over to here. So what do you think? True or false? Is A plus B equal to F?
True.
I think it's true.
Yeah, absolutely true. Let's try a different one. And let me see if I can't make this a little bit bigger here for us. Not doing a great job. All right, so I should be able to do better than this. Let me see if I can't. There. That's a little bit easier to read. So we want to see, does B equal G minus H plus C? So first of all, let's take a look at B. All right, B takes us from here to here. Does that equal G minus H plus C? Well, if we were to do G, then G would take us where? G would take us, starting at this point, it would take us down. And then what's next? Minus H, right? Minus H. If H goes this direction, that is, starts out here and goes to here, what's minus H going to look like? Can anyone envision what minus H is going to be?
That'd be the equivalent of F.
Yeah, it looks like it'd be, well, minus H is going to point in the opposite direction. In fact, tell you what we can do if you want to is we can put in some numbers here. So if we started at this point, then G would be the vector 0, -3. And then starting at the tip of H, you're going to move 1, 2, 3, 4, 5, 6 places to the left. So H would be -6 and 0. And finally, vector C, if you were to start out here at this point right here and move in direction C, what would be a way to write the vector C? What coordinates should I give it? Well, are you moving any in the X direction? No. It's just strictly in the Y direction. How far are you moving in the Y direction?
It looks like 3.
Yeah, 3. So these would be your points, or these would be your vectors. We want to calculate G minus H plus C. So it's going to be 0, -3 minus -6, 0 plus 0, 3. If I distribute that negative sign, this becomes 0, -3 plus 6, 0 plus 0, 3. When I add this all up, 0 plus 6 plus 0 is 6, and -3 plus 0 plus 3 is 0. That's exactly what vector B is. You take a look back here, B starts out at this point, call it 0, 0 out of convenience, and it moves 6 spaces to the right. So G minus H plus C does equal B. Mhm. Okay, last but not least, this one right here. You've got a force of 20 newtons acting at a 30-degree angle and another force of 10 newtons acting at a 45-degree angle. We want to add those two together and see where it goes. So let's do that. Force 1 is 20 newtons. Force 2 is 10 newtons. 30 degrees and negative 45 degrees. So what I'm going to do is I'm going to turn these into component vectors and then add them. So if I want to figure out the x and y directions of this, 30 degrees, x and y, and 20, it's just the same as it was earlier. That's going to be x is going to be 30, or see, 20 times a cosine of 30. And I apologize, I should probably motivate that a little bit more. Remember, the cosine of 30 is going to be x over 20. And if you multiply both sides by 20 to solve for x, you get this. And I got to do the same thing in the y direction. Sine of 30 is going to be y over 20. Multiply both sides by 20. Sine of 30 is 1/2. So in terms of components, or in terms of vectors, I can now write this as, let's think, it'd be 10 square roots of 3 and 10. That's the motion of, or that's the component version of that vector. The other vector is moving at a negative 45-degree angle. It's going to end up being the same thing. I am going to skip a little bit here. That's going to be 10 times cosine of negative 45, which is going to be 10 times the square root of 2 over 2, or 5 square roots of 2. Likewise, when you solve for the y component, we get negative 5 square roots of 2. That's the hard part, is just finding the component version of both of these angles, or both of these vectors. So 5 square roots of 2 and negative 5 square roots of 2. To finish this up, I need to add these together. And that's the easy part. Although writing it won't be terribly easy. So 10 square roots of 3 and 10, plus 5 square roots of 2 and negative 5 square roots of 2. I think I remember seeing in the book that your answer was something pretty ugly like this: 10 square roots of 3 plus 5 square roots of 2, and 10 plus negative, or just minus, 5 square roots of 2. So you're adding the x components, and you're adding the y components. And that's your vector. That's the resultant.
So it's more so initial plus final.
Yeah, that's all you're doing, is you're just adding the x coordinates and the y coordinates. So, you know, x1 x2, y1, y2. And that's all this is x1 plus x2, y1 plus y2. You're just adding things component-wise. So it makes the calculation nice. I used to do this in a much harder way. I would complete the parallelogram, I'd use the law of cosines, etc. You know what? Can't beat this. If you need the magnitude and direction, you can get it. You know, your magnitude of a vector is just x squared plus y squared. So you can figure out how long that vector is. No problem. It'd be ugly because you have these ugly square roots, but that's okay. Let your calculator do it. You don't have to do it. Okay. Anything else on this one?